Hello, my name is Yi Wang from Mitsubishi Electric Research Labs. I'm here to present Learning to Modulate for Non-coherent MIMO, and this is joint work of Toshiaki Koike-Akino. The topic of our work is to apply machine learning to design modulation and signal detection schemes while targeting the non-coherent MIMO channel. A recent trend in the literature is the design encoder and decoder pairs with deep neural networks. This concept involves a simulation-driven approach to end-to-end encoder and decoder optimization, where the objective of minimizing cross-entropy loss corresponds to maximizing mutual information. However, while our work considers deep neural network-based approaches, we also consider approaches that completely avoid the use of deep neural networks while still providing the simulation-driven end-to-end optimization. Our schemes result in learned designs for space-time constellations that can actually outperform some traditional designs at some SNR regimes. We showed that DNNs can be avoided altogether while keeping similar performance. We also demonstrate the feasibility of communication over the non-coherent MIMO channel while using as few as 2 time slots. In the non-coherent MIMO channel, a signal X is sent over M transmitter antennas and over L time slots. The signal is affected by an unknown block fading channel H and Gaussian noise Z, where the terms of H and Z are IID complex Gaussian. The signal is power constrained such that the average SNR is given by 1 over sigma squared. At the receiver, Y is received on NRX antennas. Our goal is to design a k-bit modulation scheme that maps the message into the signal X to be transmitted over the non-coherent MIMO channel, and then a corresponding decoding scheme that recovers the original message. In our approach, we consider an encoder where the signal constellation is captured by a lookup table. For a small number of bits k, using a lookup table is the most efficient and effective way of doing this, since the encoder can be fully captured by the table C of these dimensions. The tensor C fully parameterize all possible codebooks, but for power efficiency, we'll subtract out the centroid from that to get a centered constellation and also normalize the average power of the codebook to keep with the power constraint. For a given message, the signal X is selected from this normalized and centered tensor. A common alternative seen in the literature is to apply a deep neural network as the encoder with using one hot encoding of the message as the input. However, this vastly overparameterizes the codebook with extraneous layers. Using a DNN encoder with a binary input encoding would help scale better for large K. However, we're focused on a small K regime. Our work employs a lookup table to avoid having to use a DNN for encoding altogether. We consider 2 types of decoders. One is based on deep neural networks, and the other completely avoids deep neural networks altogether. Both are soft decision decoders that output unnormalized log likelihoods for each message. If you take these outputs and apply the softmax operation, this yields an approximation of the posterior of the message given the received signal Y. Also, in both cases, our decoders are parameterized by parameter theta. In the case of a neural network decoder, theta represents all of the network parameters. We consider specifically a multi-layer perceptron and a residual multi-layer perceptron architectures. And in the neural network decoder case, the decoder is blindly trained end-to-end with just a cross-entropy loss with respect to recovering the message. The alternative decoder that we consider is what we call a pseudo maximum likelihood decoder. And this is based on the maximum likelihood decoding rule for orthonormal codes. If the code words were orthonormal, the correlation of the received signal Y with each code word would be proportional to the unnormalized log likelihood of the received signal given M. Hence, inspired by this, our soft decision pseudo-ML decoder simply outputs this correlation scaled by a parameter theta that captures the confidence of this decision. which will then be tuned during learning. However, this pseudo ML decoder requires an additional codebook orthonormality constraint that we'll have to enforce during training as well. Our general approach is to apply end-to-end training with respect to cross-entropy loss, where the encoder and decoder, parameterized by C and theta respectively, are both optimized to minimize the cross-entropy loss. Minimizing the cross-entropy loss is equivalent to maximizing the mutual information, since the cross-entropy loss is equal to the conditional entropy of the message given y plus this KL term, which captures the distance between the proximate posterior produced by the decoder versus the actual posterior of the message given the signal. Hence, training should minimize cross-entropy loss toward the lower bound of the conditional entropy of m given y. Further, since the conditional entropy is the complement of the mutual information with respect to a constant entropy on the message, which is equal to k, minimizing this cross-entropy loss is essentially maximizing a variational lower bound on the mutual information. For the pseudo-ML decoder, we also have to enforce an orthonormality constraint on the codebook, which we do so with a soft penalty on how much the code words deviate from orthonormality. Note that we multiplicatively combine this penalty term with the main cross-entropy loss term. This is due to these terms having vastly different scales and learning curves, and we found that combining them multiplicatively worked much better than additively in experiments. In our experiments, we're working with a non-coherent MIMO channel, and we consider schemes that map 2, 4, 6, or 8 bits over 2 or 4 time slots. We consider 2, 3, or 4 receiver antennas, and we consider either the same number of transmit antennas when the number of time slots is equal to 4, or we leave the number of transmit antennas equal to 2 for when the time slots is equal to 2. We optimized encoder and decoders over a large range of hyperparameters to find systems that worked well. For the neural network-based decoders with the MLP architecture, we varied both the depth and the width of fully connected layers. The residual MLP architecture is similar to MLP, except with additional skip connections and batch normalizations. For the pseudo-ML decoder, we varied the lambda parameter controlling the code orthonormality. We found that we had to search over a large range of hyperparameters, since sometimes the training would fail with an encoder-decoder pair that did not perform well. We compared the performance of our codes with codes analytically constructed by Liang and Xia. It's worth noting that existing analytical code constructions based on Grassmannian monopods require that the number of time slots be larger than the number of transmit antennas. Our learning-based approach demonstrates a novel feasibility of handling 2 time slots and only 2 transmit antennas at the same time. Also, as we mentioned earlier, since cross-entropy loss is related to mutual information, it can be used to approximate a lower bound on throughput. We compare the throughput of the codes that we design to the theoretical capacity bounds found in the literature by Yang, de Risi, and Riegler. This slide compares our code designs for 4 time slots and 2x2 transmit and receiver antennas in comparison to the baseline approach by Liang and Xia. Here in these plots, across different colors, the number of bits is varied, and across the weight of the lines, the scheme is varied. So the solid line represents the baseline performance of the Liang and Xia codes, and the other curves of the same color represent the comparison to our schemes based on either the neural network decoder or the pseudo ML decoder. We find that in some regimes, our codes can significantly outperform these baseline approach. In this figure, we focus specifically on the performance of our neural network-based decoder for 4 time slots, as we both vary the number of bits and the number of transmit and receive antennas. Here, we compare the estimated throughput of the same codes with respect to the theoretical capacity lower bounds seen in the literature. We know that our schemes sometimes closely approach or even exceed the theoretical lower bounds. However, this just means that we have found a tighter lower bound, which is not too surprising since the theoretical lower bounds are known not to be tight at the low SNR regime. Here we present the performance of our systems using only as few as 2 time slots. We demonstrate that this learning-based approach can still feasibly achieve communication over non-coherent MIMO in this challenging regime. Similarly as before, we also compared the estimated throughput of our systems with respect to the theoretical capacity bounds. In this figure, we consider the performance of the pseudo ML-based decoder, which is a system that avoids using neural networks altogether. This is the case for L equals 4 time slots. We know that the performance here is generally similar to the neural network-based decoders. However, there are some cases where the optimization failed to find a code that did not observe an error for, which can be seen in some of these red curves. Similarly as before, here are the comparison of the throughput of these systems with respect to the theoretical lower bounds. This slide shows an example of an optimized codebook found via the pseudo ML decoder for encoding 2 bits over 4 time slots and in a 4x4 transmit and receiver antenna situation. In these figures, each row corresponds to one of the antennas, and each column corresponds to a time slot. In summary, we applied learning to the design of the modulation and detection schemes for the non-coherent MIMO channel. This involves taking a simulation-driven end-to-end learning approach to optimizing the space-time signal constellations and the corresponding decoder. We know that minimizing the cross-entropy loss corresponds to maximizing mutual information of the system. We offer 2 approaches, one that uses a DNN-based decoder, and then the other that offers a completely DNN-free system. We show that learning schemes in this way can outperform some traditional schemes in the literature at some SNRs. We also note that deep neural networks can be avoided altogether while still keeping similar performance. Further, our results demonstrate that non-coherent MIMO communication is feasible even with only as few as 2 time slots. Thank you for your time.